Hello, and welcome to Festival of the Mind 2020. Thank you very much for joining us this evening. My name is Paul Evans, and I'm an artist, and this is Andrew Parnell. So I've described myself in one word, Andrew. How would you describe yourself?
I'm a scientist. That's my vocation.
Splendid. So artists and scientists working together, which we have been for about 4 years now. I'll talk more about how we started collaborating and about our collaborations as the talk goes on. First of all, I'll introduce our project, Nanocade, which consists of a series of artworks that we've developed in collaboration between ourselves, often with the help of Human VR, the Sheffield-based design company. So these artworks that we've been working on have emerged over a period of discussion that's taken place since 2016, when I started working with Andrew on our first project for the Festival of the Mind, and I'll come back to that project in a little while. Over the last 4 years, I've had the pleasure of working with Andrew and his colleagues in the Department of Physics and Astronomy in the University of Sheffield, kind of what we might call an extended artist residency, if you like. And during this presentation, we'll look at the background to our work, examine some of the outputs from our discussions, the creative outputs, and explore a few general ideas about nature, culture, art and science. I won't be showing any video this evening. I've got a reason for that. My reason really is that I think when people see video or clips, they kind of think they've seen the thing and that they don't get the thing itself, and they don't go back to the full artwork. So again, this is something I'll talk more about in a little while. A few of the ideas behind this talk were developed in our previous presentation at the Millennium Galleries as part of the Ruskin in Sheffield programme a couple of years ago. And I think it's kind of quite hard to discuss art and nature in Sheffield without reflecting on Ruskin. And broadly, our discussion will be about art and nature, won't it, really?
I think so, yeah.
So John Ruskin, the leading art critic of the Victorian era, an accomplished artist himself, prominent social thinker, philanthropist, and founder of the Guild of St George, which is an educational charity based in Sheffield. It was set up on utopian principles in the 1870s to right some of the kind of substantial social wrongs of the day and to make the country a happier place to live in. There's also a magnificent collection called the Ruskin Collection, based in Museum Sheffield, which contains drawings, paintings, and beautiful objects from the natural world that Ruskin drew inspiration from. It's not a talk about Ruskin, by the way, but we will be dragging him into the chat. So I'm going to start this with a quote from Ruskin. "Few have reached the first level of science, wonder." That's a kind of nice word, that wonder, isn't it? It's like an old English word that kind of sums up ideas you might have about amazement or admiration, for beauty or for the unfamiliar. And avoiding the kind of obvious issue around, if you like, exclusivity that we've got here, although that exclusivity might kind of point to something aspirational, you know, in a kind of Zen sense. You know, few have reached the first level of science, this kind of Zen level of science. I was thinking, Andrew, so you've been in science a while. Have you got past the first level yet, do you think?
I don't know if I have. I still get awestruck by things I examine, study, like to try and understand. But no, I think wonder is part of what I'm interested in, understanding things that are perhaps wondrous or exciting. So I think that's what motivates me and my work, hopefully.
Do you want to tell me more about what you do?
So I'm a soft matter physicist. I've been in Sheffield for a long, long time, and I've got to work with some really great people in Sheffield and around the UK and beyond. My interest is started off looking at polymers, which are soft matter, squishy stuff, and then I've been looking more recently. I've been looking at biological materials that form colour, which we'll talk about later. So colour you find in animals like blue tits and jays, and more recently with my colleague in animal plant science, Nicola Nadu, looking at butterflies, which has been a really fun, so understanding how butterflies form these kinds of structural colours. So that's an ongoing collaboration with her. It's great fun. So it's my remit.
Okay. So my remit's rather different. I produce artworks, and I'm going to talk about a few of those. I'll just introduce a few. That's Andrew, me. One thing I need to say at the start is that apologies to people who've seen these artworks before. Can you kind of bear with me as we look at them again? And I've got a reason for looking at them again. Time always changes things, and I think that depending on the circumstance you're in, you know, we always see work anew. We always see work through the lens of our current time, whether that's the work of the ancients or the work of the great masters, or even something that you know from 10 years ago, 10 or 11 years ago, like this piece here, Leviathan, which I'm going to introduce in a moment. I'll get the picture of it up so you can see. So yeah, by which I mean our human relationship with nature has been a central part of what I've been working on for the last 11 years or so, and a questioning of this vital relationship seems to be more pertinent than ever, given the sort of catastrophic rates of extinction that we're currently responsible for. So to look at these pieces again from a while ago, so it seems it seems kind of relevant. So this is a life-size drawing of a sperm whale that I made in 2009. The idea was to get the measure of it and the measure of me. Some of the first art that was made by human beings featured charismatic mega-mammals, things like rhino, mammoth, and auroch. You know, auroch, the ancestor of the domestic cow. And I guess that this piece here kind of revisits that primacy. I'd like to state here that I did make this with my own hands using graphite on paper. It was really hard work because it was very cold. It was made in February, and the temperature in the space didn't get above 2 degrees. But the labour felt good. It was almost like a kind of ritualistic conjuring of something very special into the ex-church, which is actually a deconsecrated space in Gainsborough. Another picture of that very large drawing. There's another drawing of a whale here. This was a couple of years later from an exhibition, Millennium Gallery, called Under the Sea. And here's Rowena, the curator, next to the drawing. The title is a riff on a work by Damien Hirst, which is basically it's a lamb preserved in a vitrine, and I guess there's a pathos to that. So this piece here is called Away from the Pod, and there's a degree of pathos in the image because what we can see here is the curved dorsal fin of the orca, and this is a condition that they develop when they're in captivity. This picture is actually based on a drawing of a captive orca sort of leaping out of a pool in one of those wildlife parks. The next piece, Chaos and Theory, dates to 2010. It's my first collaboration with Human Studio, and this is a multi-channel piece, and in this basically what happens is that the species changes each time the wings of the butterfly open and close. And when I made this 10 years ago, I like to think of it as being a snapshot, really, of how we name things in the human timescale. But obviously, at the moment, you know, we've got this dreadful kind of incidence of species loss. And I think that in some ways I feel almost like you should be playing it in reverse at this current time. This project here is the first of my projects for the Festival of the Mind. I've been working on a project with the Festival of the Mind since 2012. And here I was working with Professor Tim Burkitt. And it was a multi-stranded thing. And here, I mentioned the collaboration. Well, I mentioned the collaboration with Andrew, which is going on for 4 years. I've also collaborated with Human Studio on a number of projects. Here, the collaboration was also extended to two artists, Rachel Hand and Sally Ann Roberts, and we developed some ideas about bowerbird, these bowers that are created by male bowerbirds, beautiful things. I like to describe these as arguably avian art forms. It's kind of possible that these birds are being created. And here's Sally Ann Roberts' beautiful bower just in Weston Park. As I say, this project was multi-stranded, and there's a wonderful thing, worth checking this website out, which is a series of haiku that basically we commissioned 10 writers to produce haiku based on bird calls and song, and then we tweeted them at dawn. This was a project with Brian Lewis from Longbarrow Press, and Brian diligently tweeted these bird songs at dawn, and they added up to a kind of wonderful dawn chorus. I'll read one of these out. A young blackbird tips the lovely jug of himself. His song spills through woods. I like that because it's a beautiful word image. It's got a kind of liquidity to it, and also it spills through the woods, but it spills off your tongue as well. It's got fantastic materiality, this haiku. So, in haiku terms, we'll be calling this a cutting point now, because what we're going to do is we're going to kind of, if you like, there's a sort of rupture in the idea, and we're going to throw forward a provocation. So, Andrew, does science rob nature of its mystery and beauty?
I don't think so. I mean, I think this is a very sort of antiquated view of the world, to think that, you know, just because something's mysterious and beautiful, that, it's somehow special. I think, to my mind, things can be special, and we can understand them more than we did 200-300 years ago. So I think understanding, how a bacteria works, or how a flower grows, takes sunlight and turns that into fuel. I think that's quite an important thing for us to know. But it doesn't make out the fact that, that biological organism has grown and developed and evolved over millennia. So I think, to my mind, that's still very special. And we are the only planet that we know of in the universe where this has happened. So I think that does make it interesting, and it makes us think about our place as well. So I think understanding doesn't detract from beauty and the form. Probably what is interesting about the world that we live in is that most things on this planet are probably unique, and that's probably harks back to what you said about extinction. And I think we need to think and protect what we have currently, and for the future of the planet as well. So yeah, no, I don't think it does.
So I'm going to read you a little bit more poetry, Andrew.
Go on then.
So this comes from The Tables Turned by William Wordsworth, the very famous romantic poet, who pretty much coined the phrase, "Let nature be your teacher." And this was written in 1798. And I'll just read it out and see what you think of this. So, sweet is the law which nature brings. Our meddling intellect misshapes the beauteous forms of things we murder to dissect. How do you feel about that?
I think it's counter to what we've talked about Ruskin, and we'll come on to more Ruskin quotes, where I think they're at odds in terms of trying to understand what science is and what science can offer to humanity. No one would argue that a vaccine for COVID-19 would be a wondrous thing, and I think even William Wordsworth would salute that kind of thing. So science is at one point dangerous. We think of things like nuclear weapons, but we also think of the advantages of science from health, well-being, and education for people to raise them out of poverty. So I think science and understanding is key to understanding other cultures, and I think I think this is William Wordsworth is wrong on many levels. Sorry. It's just old-fashioned, isn't it? So
how do you feel this relates to maybe current distrust of science? The
I'd
narratives
argue,
that are playing out.
I think it's dangerous to think about science, but I do think scientists and there are polls that say that scientists are very well trusted. But I think what's different and what's the general public misconstrue is the fact that scientists do disagree on things. You know, we have arguments with ourselves, with different communities, and often those arguments in a public forum, it's quite hard for non-experts to judge who's right, who's wrong. And I think that's where people start to think of mistrust in the general public, because the arguments are quite nuanced or quite specific. So I think, I think mistrust of scientists is maybe on the rise. I don't know, but I think as a class of society, I think we do an interesting and important role to raise health and well-being and prosperity for future generations. That should be our sort of, like you say, utopian goal to be, you know, to be a good citizens. Of science.
We'll come back to utopia in a minute, actually, because I think I encountered utopia in a kind of scientific context. But we'll come back to that in a moment. I mean, it is an alternative view to that. To dissect a flower might be as proper as to dream over it. I mean, my personal thinking about this is that there's this idea of mystery, which I think, you know, the romantics felt was being threatened, I guess, by science. But I tend to think about science almost like one of those, you know, those carved ivory Chinese puzzle balls. You know, and inside each, you know, there's layer within layer there. And the deeper you get, in a way, the kind of more mysterious it gets. You know that sort of that layering of. I mean, you might say, well, how does a plant make its energy? Well, it uses photosynthesis. You know, and then to create that photosynthetic reaction, it needs chlorophyll. You know what I mean? So it's layer upon layer and layer, and the deeper you get, I don't think the mystery, you know, in any way, kind of disappears. Okay, so we'll move on to our first project together, Andrew, in 2016.
That's a long time ago.
Quite a while ago. And this is a painting by Monet, the famous, the great Impressionist painter of light, atmosphere, atmospheric effects, a great maker of beauty. And this is dated 1869. And I think I read somewhere, I can't remember where, but I read somewhere that the painting the pheasant's feathers gave Monet great frustration. He couldn't sort of capture it in paint. There's a reason for this, isn't there, Andrew?
Yes, I mean, you and I have talked about this at length, but I think the key is the fact that, you know, the modern painting pigments don't replicate the structures that you need to create, and we'll see them in a second. But so I think he did go stir crazy in his trying to paint the pheasant, and if you see a pheasant feather close up, you see it's got this sort of metallic-like sheen to it, so it's really, and when you tilt it, you get different colours, like a rainbow effect. And the same is true of these butterflies. If you go to the Western Park Museum, there's a fantastic drawers of these butterflies. And you don't just get blues, you get all sorts of different colours, like greens as well. And these have got really fantastic, vivid metallic colours. They look, you know, like they were made in a factory or a lab somewhere. But yet they're made in a biological organism that, you know, copes with. But
they're not pigments, are they?
No, they're not pigments. They're structures. So you'll see in a minute how they're a series of mirrors, very small mirrors that have got this sort of not perfect but very very strong order. So here's the surface of one of the wings with all these little scales onto the wing. And as light hits those features, it picks out a certain wavelength of light. In this instance, you see all these, the blue light reflected back. And so here's the structures that are responsible for it. And you can start to see in the fact that there's sort of like a regular feature there. Like they look like little Christmas trees, but the spacing between the ridges in this region here. Sorry, I don't know if I can. Sorry. You can see how regular that spacing is, and we still don't quite know how these structures form. That's an ongoing interest of mine, with my colleague Nicola Nadu. But to try and understand why nature goes to this level of sophistication is also quite interesting as well. You know, why does it want to look blue? That's an interesting question in itself. maybe it wants to be seen by a mate, and also scare off predators. But so it's an interesting fact that nature's gone to all this effort to make essentially the kind of structure that you would want on your glasses or on a sun cream to reflect certain wavelengths of light so they don't damage your skin. So nature's using this kind of what we call biophotonics or photonics. It's controlling the way that and manipulating light in a way that's really very special. So if you go to a museum, like the Natural History Museum, and also the Western Park Museum, you'll see that these animals still look the same as when they were caught 100 or 200 years ago when the first species were collected and put in museums. That's because you actually have to grind up the structure to damage it. We know that pigments fade, we know that cars paint fades, they get damaged by the sunlight. These you actually have to physically destroy the structures involved there, the nanostructure, the very small structure, which is about 50 times thinner than a human hair or 50 times thinner than a banknote. These are really small structures, and nature's able to manipulate matter and form on these very small scales, which I think is a real lesson to us in terms of how to make things using water and biopolymers and not using nasty chemicals and horrendous processes. So
I think it's important, that thing about not using nasty chemicals.
I think so too, Paul. Yeah.
I mean, when I first saw these, what I saw was extraordinarily tiny sculptures, beautiful, extraordinarily tiny sculptures, and that's one of the outputs that we made happen. From this discussion, were a series of sculptures like this. These are actually printouts of those of what you've just seen there. They're 3D printouts. And we created a kind of arc which demonstrates really the way that the colour in an iridescent wing changes depending upon the angle at which you see it. So
if you're straight onto it, you see a one colour, and as you go to higher and higher angles, you start to see different colours. And at some point, like the one on the brown at the end, you won't see, you'll just see the underlying colour of the material. You won't see this reflector structure involved at all. So it's really quite a nice demonstration of the observation of this butterfly structure. It's very, very cool.
Yeah, it's a kind of magnification in a funny sort of way.
It's to bring that nanostructure into the physical world. Yeah. And also the 3D nature of it being 3D printed allows you to see and get to grips with that structure, which I think is really powerful.
And they have quite a nice tactile quality, didn't they?
I know you weren't supposed to touch them, Paul, but people did want to touch them. Yeah, exactly.
People did want to touch them. Right, okay. Okay, let's move on to this one, which is a couple of years ago, neutron spin, and we'll come to the reason for that title in a moment. Do you want to say a little bit about Richard Feynman, maybe? So
I've read some of his books, and if you do get a chance, they're very interesting. He's a very interesting character, a very multifaceted man. And his quote is, "The imagination of nature is far, far greater than the imagination of man." And I think that harks back to what Paul said about the natural world and about how we're now starting to use nature as an inspiration for new technologies and things as well. So I think we are constantly astounded by what the natural world can tell us. And so Feynman was a very famous physicist. He was involved in many different aspects of physics. He got the Nobel Prize in Physics in 1965 for his work on particle physics and understanding some of the very deep questions that were present at the time. But to my mind, what Feynman is more famous for is his 1959 lecture called "There's Plenty of Room at the Bottom," which was, at the time, it maybe took a long time to actually filter through, probably till the early 90s, where he's the daddy of the field of nanotechnology, which is what I did my master's at Sheffield and leads on the nanoscale science and technology. So his idea was that we can start to make things smaller, and we can start to make things, we can shrink the Library of Congress onto the size of a pin of a needle, and then we'll come back to pins in a minute, hark back to that. But I think his ideas were quite revolutionary, and we're starting to see, we've seen in the last 30, 40 years, you know, miniaturization of all sorts of technologies, from computer hardware, you know, from the iPhone in our pocket or whatever, that kind of thing. And he showed what was possible, or he envisaged that at a time when we could start to use nanotechnology to make new materials, new properties, graphene, that kind of thing. But he also harked to the idea of a working nanotechnology. And my colleague Richard Jones talks about this. He's moved to Manchester, about biology is a working nanotechnology. And like I said before, it assembles its cells into the complex structures we've seen in a butterfly's wing. It forms a DNA helix that's responsible for the information in our cells and our bodies, and also replicating that information. You know, we're like a working computer that can store, transfer, and transpose information sort of at will, in a very complex way that I think is very, very powerful. So he's a very important man in terms of the field of nanotechnology, I think.
Okay. So a little bit about this.
Yeah, no, this is you. I can talk about this forever, Paul. So this has been a great, fun project. So we chatted to a guy from AkzoNobel, formerly ICI, a long time ago, called Andrew Burgess and Gareth Crapper, sorry. And we were interested in understanding how to make a paint in the same way, white paint. So they make Dulux paint to AkzoNobel. How to make a white paint in the same way that a beetle would make white. So these are amongst some of the whitest beetles on the planet, and we call them ultra-white beetles. So they make really nice white scales. Still not quite sure why they're really white, but that's another story. But they do make really nice white little scales. And our aim was to try and learn from nature. And this is sort of where we came in, Paul, I think, in terms of...
Yeah, because I'd approached Richard with an idea about using the black is black, Vanta black, and then, much to my dismay, discovered that Anish Kapoor had got exclusive rights to the use of that. So I think Richard basically turned around and said, "What about the white is white?"
Indeed.
And that's kind of how we met.
Yeah. So so our aim was to understand, and like I've said before, my research and my sort of methodology is to look at form and function, to try and understand how to take what we understand about this biological structure and make it into a synthetic structure. So if you want to go on to the next one. Oh, this is where it happened. I wasn't actually involved in the experiment. I helped write the proposal with my colleague Stephanie Berg, but you actually went on the experiment, which I think was an epiphany.
It was extraordinary. Yeah. I was very, very fortunate to join Andrew's colleague Stephanie Berg while she was involved in this experiment at the synchrotron...
European Synchrotron Radiation Facility. So that's in Grenoble. And this is the X-ray synchrotron on the right in the picture, the big circle, and to the left is one of the world's most powerful research reactors for studying materials and science.
So that thing on the left is a kind of neutron imaging...
Well, no, it's a nuclear reactor.
Yeah.
Nuclear reactor that provides neutrons to scientists to study matter on many different topics. So it's very important facility.
I think it's kind of interesting because do they not use depleted warheads? Is that correct?
I don't know where they get the uranium
but
from.
I like that idea because that's like the old idea of turning swords into ploughshares or something like that.
Perhaps, yeah.
Yeah. Anyway,
it's quite an expensive thing to run. Yeah.
Anyway. Yeah, so the experiment that Stephanie was conducting was looking into... when you looked at that... I'll go back a little bit. When you look at this photo here, you can see that the beetles have these scales on their wing cases.
Elytra.
And that is basically the scale from a beetle's wing case.
So what that image doesn't quite get across to you that's projected there is the fact that not only... So some of you might have had a CT scan, in a hospital. So this is effectively a CT scan of a computed tomography scan of a single scale. And that's not just one slice. We can't actually present, we'll show you a 3D render of it. But what Stephanie was able to do was piece together on a very small scale. This is a single scale that was mounted on the end of a needle, which took a great deal of skill and patience, and use that machine in France, this marvelous machine called the tomography beamline, ID16B, to be able to use the X-rays by rotating it in the beam, you get all the different projections of these the X-ray scattering, and then you can actually back out the structure inside your beetle scale. So and there you go. There's a little slice of it, and go to the next one. And here's like a representative structure of it. What you can see is the fact that it looks quite strange. Sort of, it looks a little bit like a spongy structure, and we won't go into the details of it, but in terms of we've published a paper on this and shown that we can actually start to use just a commodity material, like some of you might remember the old acetate overhead sheets that you used to write on for presentations. And you can take a material that's actually transparent, and if you process it in a special way, or relatively special way, you can actually form a similar structure to this, to that which the beetle does. And so we can start to make things that are ultra white, and they have the same structure and length scales and morphology of the beetle scales. And surprise, surprise, they behave the same. That's the key.
Without the nasty chemicals.
Well, yeah. The key to what we were interested in was to replace a material called titanium dioxide, which is has a mammoth carbon footprint, so much so that it accounts for 3/4 of the carbon footprint of paint. So, if you could take a material that you recycle, like a plastic that we would normally throw away or burn, and you could give that a second life as a material that's a super white. And so that was our goal. So hopefully we can start to think about replacing carbon intensive materials with materials that we can recover, recycle, and process into high value goods or moderately valued goods, so we can use them.
So when I saw this, I saw a massive, great sculpture, to be honest with you. I kind of imagined something made out of stainless steel or something like that, 20 metres high, sitting outside the where is it again? The ESRF.
Yeah, or it's anywhere,
or
any
anywhere.
metropolitan centre you wanted to put it in the airport.
But there's a contradiction here in that we've been talking about materials and that trying to sort of minimise our impact, really. So instead of that, what we thought about was the possibility of doing it in virtual reality. So that's what we did. We took this three-dimensional model here, and then created a virtual reality environment. And in that virtual reality environment, what happens is you almost take the form of one of these spinning tops and kind of travel through it. And I'm going to have to say this: it does look really cool. When you travel through it, it looks magnificent. And I think there's something about the beauty of the structure that's reflected in that work.
It's a paraphrase. It's sort of a fantastic journey, a fantastic voyage, I think, through what has been a fantastic project. And I commend my colleague, Dr. Stephanie Berg, for this. This is and the paper that she published on it. But this kind of output, I think, is an amazing demonstration of what's possible. And I think by understanding form and function, you can actually, and also it's very engaging. I think the key, I think Paul can get across to you how engaging it is between, we visited schools across South Yorkshire and, East Coast, Grimsby, we've gone far and wide, and everyone has found this to be a truly mesmerising experience. And I think, that says a lot about how we are inspired by nature and form and function. To think about interacting with it as well. And like you say, we did think of this big, sterile-looking polished steel object, but it works so much better when you're immersed in it in a VR type environment, because you can look and you can interact in a way that you wouldn't be able to get inside it if it was a sculpture. So.
I agree. You can actually see a fly-through of it on the Fettle of the Mind website. So yeah, please visit that. I could have shown you fly through here, but you would have seen a clip. So the best thing to do is have a look at the website, and you'll find it there. Okay, so bringing us bang up to date now. This is something that's just been finished, which is we mentioned the ILL, didn't we? We mentioned the neutron.
Yeah.
So the neutron research facility. Now the plan was for me to go over to Delft, where they have another one of these.
Yeah.
Fantastic facilities. And the thing about Delft is, Delft has a kind of history of producing, well, this is called Delftware, and it's pottery that was produced in the 1700s, I think. And it kind of began as a replacement for porcelain that the Dutch were importing from China. For some reason, there was a breakdown in supply, and the Dutch started producing their own version of it. And it has this fantastic blue colour. And now, in spite of the fact that I couldn't go over to Delft to actually do the research, which is a real shame, but obviously COVID kind of put the end on, put the end to that idea. I had done quite a bit of work, quite a lot of research on the internet, and what I found on the internet were these fantastic images of neutron scattering. So do you want to tell me what these are?
So these are quite abstract representations of what you get from a scattering experiment. So you can think of a source of particles. So in this instance, neutrons, and you get them to impinge on your material, and by how they scatter. So if there was to be no pattern here, they would just go straight into the centre of the square, and you get no scattering. Whereas if you have a scattering, a specific size to your structure, you'll start to see spots or rings or patterns. And these seem quite abstract, but like I said, they actually tell you so much information. It's actually scary how much information there. So you get out the size of your materials, you get out, what kind of morphology is it? Is it a rod? Is it a sphere? Is it a hexagon? This kind of thing. How are these arranged together? So it's sort of such a sub-discipline in itself, analysing scattering patterns, these sort of beautiful. And I think that you can render them into amazing colours, and they do look like artworks in themselves. But this is something we can do with neutrons, and the neutrons. Why we like neutrons, we love X-rays as well. But why we like neutrons is that they have the ability to. We can use heavy water, so with deuterium, and we can start to play games and make things invisible. So if you get a glass rod, and you put it into water or like corn syrup, you can make the glass rod disappear. And with neutrons, you can start to play those kinds of experiments. So you can start to, if you know that something is composed of two different materials, you can make one of them invisible, and you can start to look at just one component. So it's really quite a powerful way of looking at biological structures where you wouldn't get much scattering normally with X-rays. And you can start to see things that you wouldn't normally see. And the beauty about neutrons is that they're actually very low energy. They're very low, they're very penetrating. So you can start to look at, all sorts of weird and wonderful things that you would otherwise get damaged with X-rays. So they start to heat up with X-rays, whereas the energies are much, much lower. So, you're not actually dumping that much heat into them. So it's a really fantastic way.
Yeah. I mean, to me, they remind me. I mean, the first thing that I think about really is Islamic art or something like that. I think we're looking at the structure of the universe here. I mean, I think that's rather extraordinary, an amazing thing. So bringing those two ideas together, the idea of these beautiful neutron scattering patterns with Delft pottery, we've created this thing called the Delft service. And it's actually an animation which plays on the surface of the plate, And that's available to see at the Millennium Galleries right now. Do try it. Well, if you, I know it's tricky at the moment. If it's within your comfort zone, they put things in place so as to mitigate the risks. So if you can get down there, that would be great. Otherwise, you can see the animation on the website. So we're going to have to move on now because we've got a big journey.
Okay, yeah.
This is the final piece that we're going to talk about, harvesting light, which I think in some ways is really quite mind-blowing. Another quote from Ruskin, we want in this sad world of ours very often to see in the dark. That's the greatest gift of all, but at any rate to see, and no matter by what light, so long as we see things as they are. And I think that phrase, no matter by what light, is really, really interesting, resonates really oddly in terms of what we've been talking about, because we've been talking about methods of imaging, haven't we?
Yeah. Well,
that are very unconventional.
Yeah, so I think the key is that light, X-rays and neutrons allow us to see things on different size scales. And I think they do illuminate the world, the physical world. And by looking on those different size length scales, we start to see things and assemblies of things, and we start to see things differently and to get new insight. So I think that's key from my perspective, to be able to. It's quite a good phrase, and I like the bit at the end. So long as we see things as they are. So like we see things.
The truth.
Well, truth is an interesting question, but yeah. So we start to see things for what they are, and we start to, you saw in some of those patterns that things were a bit fuzzy, and, they weren't entirely perfect, and that's true of some of the materials that we study. They're not entirely perfect. So yeah, and I think that as long as they're good enough to do the function that they perform, that's important. So no, I like that quote. Yeah.
Okay. So light from the sun, illuminating the earth, producing beautiful atmospheric effects such as the rainbow. So what we're going to take you on now is very, very quick kind of,
Whistle stop turning.
quick but rather massive journey. So what we're looking at here is the sun, our nearest star, 4.6 billion years old and 150 million kilometres away. This massive fusion reactor wherein, tell me what happens in the sun.
It fuses things together and creates lots of energy. I mean, it is the source of the mother of our all our energy needs, and that's the key for us. I think it provides, the food that we eat, the sunshine, the heat, the temp. We wouldn't have a habitable planet if we didn't have the sun. One day it will expand and destroy the world probably, but that's a long way off. I keep telling my daughter, but this kind of it is the provider of all our energy needs, and even our fossil fuel needs was provided by that kind of that's buried sunshine. So that's all come from the sun. So it's a really important provider of heat, energy, and liquid water, which is I think is again pivotal for biology. So
working with Human Studio again, we've created this piece called Harvesting Light, which is another fantastic journey from the sun to the earth. We begin in the sun where light is generated. We travel across that intervening, how many million? 150 million kilometres?
8 minutes, 19 seconds.
8 minutes?
19 seconds.
19 seconds for that journey to take place. Here we've got a photon here, a particle wave entering a solar cell. And here's some amazing scientific magic. Do you want to explain it?
It's not magic, Paul. It's basically about harvesting more light and turning that into energy. So, splitting a photon that wouldn't normally be absorbed by a solar cell into two photons that can be absorbed. And I think that kind of process is very important. And you can start to see that what my colleagues Richard Jones and Mike Weir and Tony Ryan have been doing at Sheffield with collaborators at Cambridge is to try and understand how we could start to process these materials that could turn, conventionally we have silicon solar cells. If you could paint some of these materials on top of a silicon solar cell, you could boost the efficiency by quite a considerable margin. So I think key to that would be understanding, just painting this layer on top of of the material on top of the conventional solar cell. So that would be a really important way of boosting that efficiency.
I think what's important to remember here is that basically you've got one photon here essentially in the solar cell, and that's doubled?
Yes, it's split into two.
Split into two. So that photon is in two places at the same time, is that right?
I'm not sure about that. No, it does split into, you know, that's essentially what the quantum dot is mediating that process.
And it's actually doubling the yield as well, isn't it? So that's what
normally the energy would be lost as heat, and I think that process is what's the important bit. Harvesting the waste heat and turning that into again, usable energy.
Another useful project that hopefully will lead to some real benefit to the world. And that's the in a way that's the photon entering the traditional
solar cell.
Solar cell. Okay, so how do we sum this up? We're going to go to one last quote from John Ruskin, and I do quite like this quote. The real scientific person is the one who can embrace not only the laws that be, but who can feel to the full the beauty and truth of all that nature has to show. Anyway, I thought I'd try a little thought experiment with this. And with apologies to John Ruskin, I've sort of changed this so that I've made the terms artist and scientific person kind of interchangeable. So the real artist or scientific person is one who can embrace not only the laws that be, but who can feel to the full the beauty and truth of all that nature has to show. I'm going to qualify this because I know that a lot of art, in a funny sort of way, isn't really about nature. It's about culture, or it's about art. Actually, a lot of art is about art. But as I sort of said at the beginning, I mean, my principal interest is our relationship with nature, and So with that qualification in mind, I do kind of feel that there is something about revealing more about the world, whether that is the truth or whether really it's making it more engaging or more easy to kind of understand in a way. Because I think this is the thing about understanding, isn't it? I mean, because we've been bandying that word around, haven't we? And I think that quite often when I think about understanding, I'm thinking about more of the sort of sympathetic understanding kind of meaning of that word. Or I'm going to take it back to its origins, where it meant to kind of understand, which meant to stand amongst. Do you know what I mean? And I think that's what's been great about my journey in science is to stand amongst you wonderful scientists. And going back to that notion of utopia, when I went to the ASRF, there was people there from all around the world, and I remember talking to one of the people there, and she was saying that she felt it was like working on the bridge of the Starship Enterprise. Do you know what I mean? And I think there is something utopian about that. Do you know what I mean? That kind of international shared enterprise to basically just move things forward. You know what I mean?
I think that's something that I do enjoy. I think the fact that you get to work with some very clever people who are highly motivated to understand and to push things forward in a way that is really good fun. And I think it is a journey, and I think it has its ups and downs as does all pursuits. But I think it's very rewarding in many fronts. So I think it's a fun. Fantastic journey, yes. All right.
Okay, well, thank you very much for listening to us and for joining us this afternoon. I think we've got time for a few questions.
We do have a few questions, Paul. I've got to read them out, actually. I've just been handed this thing. I have a question for both Paul and Andrew. As an artist and a physicist, how do your ways of seeing the world differ? And in what ways are they the same? I think my ways of seeing art, my personal way of seeing the world is to use a lot of different techniques, a lot of different experimental scientific techniques, which you have been fortunate enough to enjoy and experience. I think we spent time I've never been to your studio, Paul. That's my.
Oh, right. We'll
Yeah,
mention
no,
it.
I've never been. I've never been in, but we have. Paul's been involved in experiments, as you discussed, as well as other. You know, we spent time in the lab doing stuff together. So I think we have actually had a good back and forth in that sense. But we've been involved in the creative process to some extent. Or, you know, we've discussed, and I think the key from Paul's aspect is he's always tried to keep the science has been at the forefront, and I think that's what's really key to my mind. It's not just window dressing, it's actually really the science in the visuals is really important. I mean, they are in some sense very abstract, but the science is key, and I think that's actually really important to us to be able to demonstrate.
Well, I think it's a little bit about communication. I think that's what I've tried to do, is to communicate enthusiasm. You know, and I think that's a really powerful thing. And also, I guess, to try and, to try and make it. I think beauty is an engaging thing. It's maybe, it's a complex idea, but I think that to produce something, I think that has a kind of emotional affect that makes people respond in a certain way. I mean, to be honest, I do get quite a kind of buzz out of seeing that young person putting the headset on, and when they say "wow," I feel that in a way my job's done. Do you know what I mean?
Yeah, it's a terrible shame that we can't let some of you experience the visuals, the VR experience currently. But I'm sure when things do change, we will be doing something again. And I think, it's to see children, to see pensioners, get such a buzz out of it as well. I think it spans the age groups. Those sort of fantastic journeys are really important to remind people why, art and science together can provide a way of communicating, but also inspiring people to think about things that they haven't thought about before. Yeah. There's a couple more questions I'm going to come on to now. Question 2, similar to the first question, how have either of your approaches to your own practices changed or shifted in any way since your collaboration? Did you get that?
Yeah, I did. Yeah.
So I think my personal belief is that I've tried to get better at explaining things and tried to use less jargon, because I think it detracts from the science. Sometimes it's hard not to use the jargon, but I think it's actually really it's really important to try and just break things down, not to make things simplistic, but to try and explain them in a way that's as it needs to be. It doesn't need to be overcomplicated. So I think sometimes people can do that, and I think if you're trying to explain complex ideas in a way that's people can understand, that's a hard thing to do. So, but I don't know what you feel, Paul.
Yeah, I mean, I think it's a very similar thing, really, which is to try and make something. I mean, again, going back to beauty, there's a kind of beauty in simplicity. Do you know what I mean? So we might be dealing with really quite complex ideas. And I mean, people have said to me, that's really difficult to understand. But again, it's like, you may be thinking about different kinds of understanding. Do you know what I mean? Yeah. And in actual fact, the sort of sympathetic understanding of it isn't so difficult. In actual fact, it's quite transparent and fills me with excitement. Do you know what I mean? And that's the excitement I kind of want to communicate in the work, really. I also think there's a bit of a shared space, really. Going back to that first question again, I think that we've managed to occupy a kind of shared mental space. You know what I mean?
Yeah.
While we've been working.
It's been a lot of conversations, a lot of good conversations,
and also bringing in other people we've collaborated with. Do you know what I mean?
We've got the final question, Paul. So, thinking about fractals, that is self-similar patterns recurring at different scales. Have you seen anything especially interesting or elegant through your work? So, can you just pop back to the Beetle scale, internal structure? Keep going. I think we've not got very long, but I'll just want to show, yeah. Keep going. Yeah, so, yeah, I would leave that up. But I think I'll go forward one more actually to the there. So the nanostructure that's involved in this beetle, the underlying physics of this spinodal phase separation is seen on many different length scales. It's seen, in the cosmos. It's seen, in your oil and vinegar dressing, that kind of thing. It's a really, it's about things that mix and intermix. So I think it is, yeah. You do see patterns, and you do see similar structures. We think of, fractals like the Mandelbrot set. You start to see, recurring structures. So, yeah, there's some sort of universal morphologies and patterns that we see in these biological structures. So, yeah, which is intriguing. I think.
I think people do respond to patterns in quite an interesting way. I mean, it's almost like a kind of it's almost a state, isn't it? It induces a kind of state of mind, doesn't it? Which I think is kind of an aesthetic state of mind, really. I was going to say, we've got another podcast due for release on Monday the 21st at 10 a.m, which is called Light, the Universe and Everything. And that's got some questions which were crowdsourced from various members of the public. It's another kind of light journey. In a way, it revisits that light journey from the... it extends it, really. So extends it from the very boundary of the universe down to the very, very smallest thing. And I think an interesting thing there, am I right in thinking that we're bang in the middle in terms of our size?
I'm not sure, Paul. You put me on the spot there.
I did read that somewhere.
Well, yeah,
Maybe that's true.
I'm not sure.
And if you want to basically check up on more information, there's lots more information on these websites about the projects that Andrew and I have been working on over the past 4 years. And I just want to say thank you very much again for joining us this afternoon, and hope you enjoy the rest of the festival.
Thank you.
The team have put in a huge amount of effort, so please try and support it. There's 30-odd projects to look at. It's an amazing thing. And thank you very much.
Thank you. Thanks very much.